Right, so now for one of the more important things ever, the properties of logarithms. Okay, so here's all the rules for logarithms, and we'll talk more about some specific ones in a second. Now I know right here has log but that's log base a. So I just decided to write out the base right next to the log, just so that we all understand. And plus it's kind of hard to write and keep in one screen log base a a whole bunch of times. So when you see this log a, this is the base, that first number is the base, the second number is the number of the log. Okay, so that is the pretty simple stuff. Okay, so here's some things. First off, the change of base formula is this. Okay, log of a of x, if I needed to calculate this on my calculator that didn't have a subscript formula, okay, but basically it's the common log of x divided by the common log of a is how I actually do that. And that's how I used to have to do it on old school calculators. Okay, so that's change of base formula. And that's also how they had to graph and stuff. They had to go, oh, if it's log base 2 of 12, I would have to go log of 12 divided by log of 2 and graph that, and that would actually be my actual function. Okay, alright, now up here I've kind of written some things up here before I've shown the actual formula. Up here, if you go from left to right, you are expanding the logarithm. If you go from right to left, you are contracting the logarithm. Okay, but here's what it's actually saying. Okay, log base a of m times n is log base a of m plus log base a of n. And so the log of the multiplication is the sum of the logs. Simple as that. Alright, log base a of m divided by n is equal to log base a of m minus log base a of n. Okay, the log of the division, log of a division, is the difference of the logs. Okay, log base a of 1 over n is the same as the negative of log of base a of n. And this just follows from the previous division rule because log base a of 1 is 0. Okay. Alright, and log base a of m to the r power is the same as if I took that r and multiplied it in the front of log base a of m. And so the log of m with an exponent of r is r times the log of m. So I can rewrite it either way. Okay, and which situation do you use? Depends on if you're expanding, you go from left to right. If you're contracting, you go from right to left. And if you don't know if you're expanding or contracting, you use which one suits you the best. Alright, also some other rules that you just want to remember for logs. Log base a of 1 is equal to 0 because a to the 0 is equal to 1. Log base a of a is equal to 1 because a to the first is equal to a. That's pretty simple. This one's a little bit tricky for people to understand. Log base a of a to the x is x because a to the x is a to the x. Now that's one explanation of explaining it. I think the best one to use is probably this rule right here. When you're raising something to a power, you bring it down to the front. Okay, so that's why this x gets brought down over here, and then this log base a, if you remember, it turns into a 1 up here. So it's x times 1, so it just becomes x. So it's a good way of canceling out some logs when you don't need them, and it's a good way just to rewrite some stuff. Okay. Alright, so when in doubt, when you're expanding or whether you're contracting, these are good rules to follow, all of these to working with logs. Change the base, just pretty simple stuff to work with. Okay, let's go to another page and let's start practice. Alright, now, log base 4 of 32 minus log base 4 of, let's say 16, does not turn into log base 4 of 16. This actually turns into log base 4 of 2. Why? Because since I am working with this, okay, since I'm working with subtraction, I divide the 2. So this case, this is going to be right here. This is going to be actually 32 divided by 16. Okay, so that's what that actually is. All right. Now, if I did log base, well, let's just do common log. Log of 12 plus log of 3. That does not turn into log of 15. That turns into log of 36. Why? Because it's 12 times 3. You have to remember the rules are kind of backwards from what you're used to. And the reason why the rules are kind of like that is the rules are kind of like the exponent rules. X to the 5th times x to the 7th is x to the 12th. You think you would multiply them, but you add them. And here you think you would subtract them, but you divide them. You think you would add them, but you would times them. So it's just backwards. It works just like the exponent rules, except backwards from the logic you're used to. Okay? Now let me show you some trick questions. Alright, let's let log base b of 2 equal this decimal. So this is the decimal it is. Log base b of 3b, this decimal, and log base b of 5b, this decimal. Use these values, evaluate log base b of 10. Okay? Well, if we think about that, 2 times 5 would be 10. So in other words, log base b of 10 is equal to log base b of 2 plus log base b of 5. And look at that. We know those decimals. Those decimals will actually be 0.3869 plus 0.8982, and that will actually be 1.2851. Okay, and this is actually how mathematicians and engineers had to do math in the past, especially with logs, before graphing calculators and before advanced calculators, was because they had to work with this information. They had to actually find creative ways around it, and logs were sometimes the best way to do it. Okay, so what you do is you actually use the decimals that represent the log bases, and you can add them together for different types of combinations. So for like example, if we did log base b of 9, yeah, let's do 9. Okay, that would be the same as if I did log base b of 3 squared. Okay, and if you remember the rule for when you raise something to a power, you just bring it to the front and you multiply it. And so what this actually becomes is 2 times log base b of 3, which is 2 times, what is it, 0.6131, and that turns into 1.2262. Okay, and that's the gorgeous thing about this, is that I can actually re-represent this stuff. Okay, like for example, if I wanted to do this one, let's do log base b of, I believe it's what, 7.5? 7.5. What I can do is I can expand this to be parentheses log base b of 5. Well, it'd be probably 15. Now let's put in, let's put in parentheses. Log base, I'm trying to think about how to write this out. Log base b of 5 times 3, and then I divide that by 2. Okay? Alright? So I thought about how to represent 7.5 with 2, 3, and 5. And the best way is to go 5 times 3, which is 15, divided by 2, which is 7.5. Now, I can rewrite this as log base b of 5 times 3 minus log base b of 2. Okay, so that's that one right there. And then I rewrite that first one as log base b of 5 plus log base b of 3 minus log base b of 2. And it's so amazing just to see where logs actually came into play in the past and everything. Okay, and so if we work that all out, all those decimals, what is that? 0.3 oh, sorry, that's 2. 8982 plus 0.6131 minus 0.3869, and this would actually all equal 1.1244. Okay, and this is how they had to do it in the past. This was so cool how they were actually able to work with this stuff. It was just amazing of how it worked. Okay. All right. Now here's the really cool thing. Let's say we did log base b of 6. Let's say we wanted to find 6. That would be basically log base b of 2 plus log base b of 3. Why? Because 3 times 2 3 times 2, whoops, that's a 33, didn't realize that. So 3 times 2, so I break it apart into addition. Well, when I add these two together, guess what I get? 1.000. So that must mean that log base 6 of 6 is equal to 1.000. So that must mean that b is actually equal to 6. So if you mess around with this long enough and you find some numbers that add up to 1, you can actually find out what the missing base is going to be. Okay, so that's some really cool stuff about it. Okay.